Hi, thanks for joining the presentation. My name is Bibek Poudel and I'm a third year PhD student at the University of Memphis. This is the work that I did with my advisor, Dr. Weizhi Lee. Deep learning based models are being widely adopted in intelligent transport systems, and this is primarily because of their performance in terms of accuracy. In this work, we try to shift the focus of such deep learning based models from their accuracy to their robustness under some interesting attack scenarios. So I'll briefly motivate the work that we did, followed by talking a little bit about the task in which the deep learning based models are deployed. And before I conclude with some future directions to the work, I'll briefly present the results that we got. Traffic state and traffic state prediction is a well studied topic in both intelligent transport and transportation engineering. And there's value in performing this study because, in the short term, it can help us forecast the daily commute demands and demands of an upcoming holiday or an event. Whereas on the long term, it can help us forecast the growth that a particular stretch of road or a highway needs. And both traditional and deep learning based models have been used to perform this prediction, where deep learning based models give state of the art accuracy. But from other domains like image classification, we know that deep learning based models are vulnerable to adversarial examples, which can degrade their performance severely. So, before we think about deploying such deep learning based models in the wild, we need their robustness to be evaluated. The traffic state prediction task could be a single node, a single step task, where in this image on the right, we can see that there's a certain area of a city where we have multiple roads, and in one of those roads, there's a node which collects traffic data, for example, traffic flow for each time step, where a time step could be 1 hour, so that the input data that is collected over 12 hours, and the prediction could be made in the 13th hour or one time step into the future, making it a single node, a single step traffic state prediction. This can be scaled all the way up to a network-wide multi-step traffic state prediction where an entire city or an area is covered by multiple nodes which collect data multiple time steps into the past to make prediction on multiple time steps into the future, where in this diagram here the input and output is just shown for one node, but this can occur for multiple nodes. Some of the traditional models that are used for this network-wide multi-step traffic state prediction task are linear regression, which takes the historical data as input to fit a line and then extrapolate that line to make a prediction into the future. A historical average, which looks at the same time step in the same period in the past and takes the average to make a prediction. For example, to make a prediction on a Tuesday 3 p.m., it will look at multiple Tuesdays and multiple 3 p.m.s in the past to take an average. Also, the deep learning based techniques that have been used for this task are the DCRNN model, which uses diffusion convolution in an encoder-decoder based recurrent neural network architecture. And this model came out in 2018 and was considered as state of the art until it was surpassed by the GCGRN model that is still under review in 2021, and that uses gated recurrent units. So the models that we considered for our evaluations are the models that are highlighted in the red. Let's get into the methodology and first talk about the adversarial attacks. So to illustrate the purpose here, I will consider a task of traffic sign classification. So although the image on the left and the image on the right are seemingly the same image to a human eye, they behave very differently when fed to a state-of-the-art deep learning-based traffic sign classifier model. And the image on the right has been crafted by adding some minimal and intentional perturbations to the image on the left, where minimal means that the perturbations that are added are so small that they are very hard to distinguish, and intentional as in they are not entirely random, they have some inherent structure to it, and most probably they are generated by an algorithm. And the output of a state-of-the-art deep learning based image traffic sign classifier for this image is correctly classified as a stop sign, whereas the image on the right is classified as a speed limit 45 sign. And if such a model was to be a part of some decision stack of a self-driving car, this could have some fatal consequences. So the specific attack scenario that we consider in our evaluations is known as black box attack, where a black box means that the attacker does not have access to any of the model parameters, the trained model weights, or the data that was used to train the model, but the attacker does have access to querying the model, as in passing some inputs to the model and getting its predictions. Let's see the scenario here. Consider that a model named target model is the model that the attacker wants to attack, and for that purpose the attacker takes a bunch of inputs and feed it to the model to get the predictions. And now, using the supervised dataset of the input and predictions of the target model, the attacker can train another model known as a substitute model. And now when a substitute model is trained and adversarial examples are crafted for the substitute model, which mimics the behavior of the target model, these adversarial examples can be expected to work for the target model as well. The attack algorithms that we consider use gradient information in order to maximize the error of the model, and perhaps the most popular one in this regime is the fast gradient sign method, which is a single step, computationally very efficient, fast method, whereas a basic iterative method is an iterative version of the fast gradient sign method, which can yield more adversarial examples that are more closer to the original signal, but requires more computation to do so. The dataset that we used came from the Caltrans PEMS system. The image on the right shows Los Angeles, where irrespective of the color of the dot, each dot represents a node where traffic flow data was collected in an hourly fashion, so that when the data was collected for a period of 6 months, we have a total of 13,000 data points. And there are a total of 150 nodes in our consideration. The data that we obtained from the PEMS system was pre-processed into 12-hour time step windows and split into two parts. The first part was used to oracle or query the model that we wanted to attack, and using the input and prediction pairs, we trained a substitute model for each of the model that we wanted to attack, and the substitute model in our case was the ResNet 50 model. Now, using the other part of the data and the trained substitute model, we generated adversarial examples. And these adversarial examples or adversarial signals were evaluated on the target model to look at their predictions and to come up with results. Just to recap, we have 4 target models. 2 of them are traditional, the linear regression and historical average, and 2 of them are the deep learning based models, DCRNN and GCGRNN. And the attack algorithms that we use are FGSM and BIM. Now, let's look at an example here. Here, the x-axis represents the time steps, where the first 12 time steps are the input, whereas the other 12 time steps are the output, and the y-axis represents traffic flow that are normalized to the 10 power 3 values. Consider this original signal, for which the ground truth looks something like this. And the prediction of the GCGRNN model to this original signal is pretty close to the ground truth. Now, when we craft this adversarial signal using FGSM, which is again pretty close to the original signal itself, the predictions of the GCGRNN model are way off. In this image, we can see the adversarial signal that was generated by BIM and its corresponding prediction. If I go back and forth, we can see maybe around time steps 3, 4, 5, and 6 that the adversarial signal from BIM is more closer to the original signal compared to FGSM, and it still manages to produce some error in the prediction of the GCGRNN model. Now let's look at some quantitative results. Here we measure the changes that was brought to the original signal when adversarial example was crafted using one of these 2 algorithms, and also the corresponding change that was brought to the prediction when the adversarial signal was passed to the model instead of the original signal. And we do this for all the models in our consideration. First, we can see that the changes brought to the original signal by FGSM for 3 of our models is exactly the same for as indicated by this green box, whereas the changes brought to the original signal by PIM is more or less the same as seen in this black box, whereas the changes brought to the historical average model's original signal is very high. We can also see that the changes brought to the original signal by BIM is in general more smaller than the changes brought to the original signal by FGSM. And this is desired by an attacker because the attacker wants the original signal to be as close as possible to the adversarial signal. And also the attacker desires that the changes brought to the prediction be a higher value. And if we look at the changes here, the DCRNN model immediately stands out as producing the highest amount of changes to the predictions, whereas the historical average does not produce any changes. Now let's look at some root mean squared error values on the predictions of either original signals or adversarial signals from two of our algorithms. Here, the x-axis represent the root mean squared error values, whereas the y-axis represent the number of signals that lie in those particular RMSE value ranges. And the blue color represent the root mean squared error on the predictions made on the original signal, whereas the greener colors represent the RMSE values on predictions made on the corresponding adversarial signal from the two algorithms. We can see that for the GCGRN model, the RMSE error on the predictions made on original signal lie within the range, probably somewhere a little lower than 500 to 1000, whereas the error on the predictions on adversarial signals lies at a ranges up to 5000. This change is perhaps more pronounced in the DCRNN model, where between 500 and 1500 all the original signal predictions are constrained, whereas for the adversarial signal they go as high as 2000. Now for the linear regression model, at each error ranges, the values, the number of signals that lie in those error ranges is more or less the same, ranging from 1000 to a little bit higher than 3000. Whereas for the historical average, we can see that at each error range, the number of signals that lie in those particular error range is exactly the same. This means that for the historical average, the adversarial signals were not able to produce any changes to the predictions. For linear regression, there was a small amount of changes. For the DCRNN model, there was a huge amount of changes because the distribution was shifted severely to the right. Whereas for the GCGRNN model, it was somewhere between linear regression and DCRNN model. Now, to conclude, the higher accuracy brought by deep learning based models on these tasks does not necessarily correspond to a higher adversarial robustness. For the DCRNN model, we were able to degrade the performance up to 54%, whereas for some traditional models like linear regression and historical average, there was either a minimal amount of changes made to the prediction by adversarial signals, or there was simply no degradation at all. So for the future work, we have been promised this world where our cars are so smart that they can connect to some kind of a grid or a system and predict our travel demands before we even make them. But without developing some kinds of defense techniques against such adversarial attacks, that dream will be far from realized. And also, in order to extend the line of work that we did here, we could attack some connected autonomous vehicles. If you like this presentation, please consider reading our paper. And if you have any questions, please shoot me an email at this address. Thank you.